Organic reactions take place as a result of attraction between nucleophiles and electrophiles, attractions between dipoles, if you like, negatively charged intermediates or substances or species with positively charged intermediates or substances or species. But that's not the only reason why organic reactions take place. Organic reactions take place also because of orbital overlap between the homo orbital, a filled orbital from a nucleophile, and an unfilled or empty LUMO orbital in an electrophile. So it's overlap between HOMO and LUMO, if you like, HOMO-LUMO interactions between HOMO of a nucleophile and a LUMO of an electrophile. The electrophiles that we have talked about so far are exemplified by alkyl halides and carbonyl compounds. Alkyl halides are electrophilic due to inductive effect, which is a result of difference in electronegativity between the halogen and carbon that's bonded to them. This results in an unequal shift of electrons in that CX bond. Therefore, carbon that's bonded to X in alkyl halides is electrophilic, and for that it is susceptible to nucleophilic attack. Carbonyl compounds are also electrophilic. That's due to inductive withdrawal, inductive effect, which is a result of the difference in electronegativity between carbon and oxygen. Oxygen pulls electrons toward itself in that CO double bond. Not only that, there is also resonance. We will see this very shortly. Amines, ethers, alcohols, all of these are functional groups. They are functional groups because they do functions, they do chemical reactions. They do chemical reactions because of the inductive effect, because of bond polarity, because of the difference in electronegativity between carbon and the heteroatom that's bonded to it, which is a result of the difference in electronegativity, therefore an unequal shift of electrons in that C heteroatom bond. So therefore these functional groups contain polar bonds. Let's now focus a little bit on the carbonyl group. The carbonyl group is probably the most important functional group in organic chemistry. Let's write the general structure of the carbonyl group, which is something like that. This is an example of a carbonyl group. Now the carbonyl group is present not only in ketones, which are generally represented, but also in aldehydes. Not only that, the carbonyl group is present in carboxylic acids, obviously, and carboxylic acid derivatives. But what do we know about this? If you look at the carbonyl group, you will notice that carbon has a double bond with oxygen. Now carbon has a double bond with oxygen. That double bond is counted as a single effective electron pair. So therefore carbon is surrounded by 3 effective electron pairs. So that's 1, 2, 3. Oxygen also is surrounded by 3 effective electron pairs. Okay, this double bond is counted as 1. That lone pair and that one are also 2. So there are 3 electron pairs around oxygen. Therefore, the hybridization type of carbon is sp2, and so is the hybridization of oxygen, because each of these atoms is surrounded by 3 effective electron pairs. So the hybridization here is sp2, and it is also here sp2. Now, because of the hybridization type, the overall around carbon, that it is sp2, the overall arrangement of electron pairs around carbon in the carbonyl group is trigonal planar, and also the molecular shape, because there is no lone pair. Therefore, the bond angle is actually about 120 because of the trigonal planar geometry, if you like, or the trigonal planar molecular shape around carbon. Let's try to draw a picture of orbitals or a picture of bonding in the carbonyl group. For example, carbon. That's carbon. Now, we've seen already that the hybridization type is sp2. There are 3 of them, obviously, around carbon. So that's one of them. This is an sp2 hybrid orbital, and that's another, and that's a third one. So each of these orbitals is an sp2 hybrid orbital, and there are 3 of them. Well, carbon is bonded to oxygen, and the hybridization type of oxygen is also sp2. So there should be 3 of them, 3 sp2 hybrid orbitals on oxygen. And oxygen must bond with carbon. And this double bond comprises 2 types of bonds, a sigma bond and a pi bond. And you know from basic chemistry or basic bonding principles that the sigma bond is found by head-to-head overlap or end-to-end overlap between orbitals from 2 atoms. So we can draw therefore oxygen like that. So that's oxygen. Oxygen has 3 sp2 hybrid orbitals. So that's one of them. That's one hybrid orbital, sp2 hybrid orbital. That's a second, and that's a third. Now, carbon makes 2 bonds with 2 groups here, in general in carbonyl groups, okay? So if you take, for example, R, we can draw it like that, something like that. Now, this sp2 hybrid orbital will overlap with another orbital from these groups, or from hydrogen, for example, here in the case of aldehydes, and so on. Now, if you notice, the sp2 hybrid orbital from carbon overlaps with this sp2 hybrid orbital from oxygen. This is a head-to-head overlap again, or end-to-end overlap, which is represented by this point of overlap, indicative of formation of a sigma bond. So therefore, this is a sigma bond, which is formed by an overlap of an sp2 hybrid orbital from carbon with another sp2 hybrid orbital from oxygen. Now, the other sp2 hybrid orbitals on oxygen contain the lone pairs. Okay, so there are 2 electrons in that sp2 hybrid orbital, and there are 2 in the other. So what we have considered so far is only sigma bonds, but we know already that each double bond comprises a sigma bond and a pi bond. And of course, the pi bond is formed as a result of electron sharing between properly aligned p orbitals. Basically, p orbitals or orbitals that were native, orbitals that were not used in the hybridization process. So we can draw, therefore, a p orbital on oxygen to be of this type, or this shape in general, which is a dumbbell shape. So that's a p orbital on carbon, and that's the p orbital on oxygen. Now, electrons located in these p orbitals get shared by the 2 atoms, and this electron sharing is actually above and below the sigma bond, and for that, this constitutes what's called a pi bond. So that's a pi bond, the bond that's formed as a result of electron sharing of electrons, if you like, between in p orbitals, native p orbitals located in the carbon atom and the oxygen atom. But why is the carbonyl group reactive? Why is the carbonyl group electrophilic at carbon? And why is it, for example, also nucleophilic at oxygen? In other words, why is the carbonyl group reactive, whereas a carbon-carbon double bond is not as reactive? In other words, why is the carbonyl group susceptible to nucleophilic attack at this carbon, whereas a similar carbon and a carbon-carbon double bond is not? Well, that's because of the difference in electronegativity between carbon and oxygen. We can draw the carbonyl group like that again. And oxygen is more electronegative than carbon. It pulls electrons, therefore, toward itself in this CO double bond, leaving carbon with a delta positive and oxygen with a delta negative, a positive partial charge on carbon, a negative partial charge on oxygen. And this means or indicates that carbon is electrophilic, whereas oxygen is nucleophilic. This is inductive effect. Again, inductive withdrawal. We can write that down. So this is inductive withdrawal. It is withdrawal of electrons from carbon by oxygen, a result of a difference in electronegativity. negativity between oxygen and carbon. Of course, oxygen is more electronegative. Now, not only the inductive withdrawal is a reason behind the electrophilicity of carbon, it is also resonance. So we can actually draw a resonance, something like that. We break a carbon-oxygen pi bond and release the 2 electrons on oxygen. And therefore, we can draw another resonance structure, something like that. Now, there were 2 lone pairs before an oxygen. Now, that oxygen has another one, a result of release of electrons as a result of breakage of that pi bond. Now, that oxygen has 7 valence electrons. If you subtract 7 from 6, which is the number of valence electrons of oxygen in the free state, you would get a formal charge of -1. So the formal charge of oxygen in this resonance form of the carbonyl group is negative, actually, or -1. What about carbon? Well, if you look at that carbon, it has 3 valence electrons, and there are 4 valence electrons in the free state, or the free element, okay? So the formal charge must therefore be +1. It is positive, and for that reason, then, carbon is electrophilic due to resonance withdrawal. So we can label this as electrophilic. The carbon is electrophilic, and oxygen obviously is nucleophilic. So carbon is electrophilic, oxygen is nucleophilic, not only because of resonance withdrawal, as you see in front of you, but also because, or a result of, inductive withdrawal, which is also a consequence of the difference in electronegativity between oxygen and carbon, leaving a positive partial charge on carbon and a negative partial charge on oxygen. Therefore, carbon of the carbonyl group is susceptible to nucleophilic attack. Carbonyl groups are probably or arguably the most important functioning group in organic chemistry.